Everything you think you know about the solar system is wrong. Over 99.9% of it is nothing. No planets, no stars, only silence and empty space. Diagrams hide this from you because the truth doesn't fit on a page. The planets you think are close together are separated by distances so vast they shatter human intuition. Tonight, you won't just learn the true scale of the solar system, you'll feel how vast it really is. And once you do, every image of the solar system you've ever trusted will feel like a beautiful lie. Before we begin, thank you for being here. If you feel connected to this space, a simple like or subscribe would truly mean a lot. Now, let everything soften, and together we drift into space. We need to admit something right away. Our brain is lying to us about space, not on purpose, not maliciously, but in the same way a foggy window lies about the shape of a city at night, because the solar system is not just big, it is built on a kind of distance that our senses were never designed to hold. We evolved to judge the gap between two trees, the width of a river, the length of a field before the sun sets. But the moment we step into astronomy, our instincts collapse. And that collapse is not a small error, it's catastrophic. Because once we misunderstand scale, we misunderstand everything that happens out there. How hard it is to travel, how empty it really is, how isolated our world truly becomes. And this is where everything changes. Because the solar system we think we know is not the solar system that actually exists. There's a reason space feels manageable in our mind. We've been trained to see it wrong. Textbooks put the sun on one side of a page, the planets lined up beside it, all neatly spaced, like a family portrait. And we understand why they do it. They have no choice. If a book tried to show the solar system at true scale, the page wouldn't be a page anymore. It would have to become a highway. Because here's the reality most diagrams quietly erase. The average distance from Earth to the Sun is about 150 million kilometers, about 93 million miles. That number is already too large to feel. So our mind does what it always does with overwhelming data. It compresses it. It turns an abyss into something that looks walkable. But the universe doesn't care what our mind can comfortably imagine. And scientists know this. NASA, ESA, and every mission team that navigates the solar system, they don't navigate a diagram, they navigate emptiness, and that emptiness is the true architecture of space. Here's the strange part. Most of us think we understand scale because we understand size. We know the sun is huge, we know Earth is smaller, we know Jupiter is a giant, but size is the easy illusion. Distance is the real monster. Because the solar system is not just a collection of objects, it is mostly the nothing between them. And our brain keeps committing one specific mistake. We treat relative size and relative distance like they're the same kind of information. They are not. A planet can be large compared to another planet, and still be separated by a gap so wide it fractures comprehension. This is why images mislead us. We see the sun and planets drawn close together, and something inside us assumes the gap is only a few times bigger than the objects. But in the real solar system, the gaps are not a little bigger. They are grotesquely bigger. The distances dominate the story. And when we don't feel that domination, we don't truly understand the place we live. Imagine we build a solar system you can walk through. You decide. The sun will be the size of a big beach ball, about 1/2 meter wide, sitting in the middle of a field. At that scale, Earth isn't a marble. Earth becomes a peppercorn, about 4 or 5 millimeters across. The kind of thing you can lose between your fingers. Now here's where the picture collapses. That peppercorn doesn't orbit near the beach ball. It orbits about 54 meters away, roughly 177 feet. That's not a few steps. That's across a wide open field, more than half a football field. So picture it, a beach ball sun in the center, and a peppercorn Earth circling it from far away, with nothing between them but emptiness. Already, our neat textbook diagram is dead. Because in the real solar system, the space between things isn't decoration, it's the main structure. It's what the whole place is made of, and that's only the first gap, because the solar system is built from distances that get worse, and worse, and worse. Even when we use real photos, we still get tricked, because cameras have their own lies. A camera can compress distance with a long lens. It can make far things look close together. Stacked, crowded, falsely intimate. And in space photography, NASA images are often chosen for clarity, or stitched or processed, so we can see faint objects against darkness. That's not deception, it's translation. But the translation has a cost. It can make the solar system feel like a place where everything is within reach, where the planets feel like neighboring cities. Except, they're not cities. They're islands, and the ocean between them is not water, it's vacuum, it's silence, it's distance so severe that even light, moving at about 300,000 kilometers per second, about 186,000 miles per second, still needs time to cross it. Sunlight takes a little over 8 minutes to reach Earth. 8 minutes. That means when we look at the sun, we are not seeing the sun now. We are seeing the sun as it was 8 minutes ago. If the sun vanished in this moment, an impossible event in real astrophysics, but stay with the idea, we would keep seeing it, glowing calmly, for 8 minutes, as if nothing had happened. That delay is not a special effect, it's the geometry of reality. And this is why scale matters, because once we accept that delay, we start to feel the real size of our neighborhood. Our senses are brutal, practical tools. We have depth perception tuned for short distances. We judge space by comparing objects of known size, a tree, a person, a building. But in the sky, we lose all reference. No fence posts, no street lights, no familiar edges, just darkness. So our brain, desperate to form a picture, fills the void with assumptions. The planets look like points of light, so we assume they must be small in every way. We see the moon near the horizon and it looks enormous, so we assume the sky itself is a dome, close and intimate. But the sky is not a dome, it's not a ceiling, it's a direction, and beyond it is distance on a scale that violates the instincts that kept our ancestors alive. This is why we feel like the solar system is packed, because our brain cannot emotionally process the truth. Most of space is not filled with things, it is filled with absence. So let's talk about the diagrams. Most solar system diagrams are not wrong, they're incomplete, they are forced into compromise. If a diagram shows correct planet sizes, the distances become impossible to fit. If it shows correct distances, the planets become invisible. At true scale, Earth would be a speck. The asteroid belt would look like almost nothing. Jupiter would be far away, so far that on a page it would vanish. So textbooks do what they must. They pull the planets closer, like magnets on a fridge, and our mind learns that as the default reality. We absorb it when we're young, when the brain builds its first cosmic map, and then later, when someone says Mars is close, it sounds true. When someone says we'll just go to Jupiter someday, it sounds like a harder version of crossing an ocean. But those beliefs are born from a picture that had to cheat to exist, and that cheat shaped our entire imagination. This creates a bigger problem, because scale isn't just about numbers, scale is about meaning. If we believe planets are close, we believe space travel is mostly engineering. If we believe space is crowded, we believe the universe is full of places waiting for us. But the real solar system is a kind of isolation machine. It spreads objects out so widely that even the nearest neighbors are separated by emptiness that punishes the body, the machine, and the timeline. This is why missions don't zip to planets. They coast for months, for years, through blackness. This is why a spacecraft can travel faster than a rifle bullet, faster than any plane, and still take an eternity, by human standards, to cross interplanetary space. And if we don't internalize that, we misunderstand the bravery and precision behind every mission. We misunderstand what it means that humanity has touched other worlds at all, because to send anything into the solar system is to throw it into a void and hope our math holds. Scientists don't rely on intuition here. They rely on measurement. They build scale into everything: trajectories, fuel limits, communication delays, orbital timing. Einstein's work reminds us that light itself sets the speed limit of cause and effect. Stephen Hawking often spoke about how the universe resists human-scale thinking, and NASA mission teams live inside that resistance. They plan for delays. They plan for vastness. They plan for the possibility that something breaks, and the nearest help is not minutes away. It's millions of kilometers away, millions of miles away, and suddenly we feel it. The solar system isn't a place with planets. It's a place where distance is the main character. So here's the truth we need to hold on to, quietly, firmly, before we go any further. Our brain wants the solar system to be a model, compact, graspable, friendly to our imagination. But the solar system is not built for our imagination. It is built from scale so enormous that our instincts fracture, and that fracture has consequences. Because every time we picture the solar system as a tidy lineup, we are erasing the thing that defines it, the overwhelming dominance of space between objects. Not the planets, not the sun, the emptiness. This is why distance is the real physics of our cosmic neighborhood. It governs travel, it governs communication, it governs energy, it governs what is possible. And once we accept that, we're ready for the next step. And now, just for a moment, picture yourself standing on an open road at night. No buildings, no city glow, just you, and darkness, and a few distant lights. Now imagine those lights are not street lamps. They are worlds, and the space between them isn't the length of a road. It's the kind of distance that can swallow entire human histories and barely notice. That feeling in your chest, that quiet pressure, that is what real scale does to a human mind. But we haven't even reached the most disturbing part yet, because even if we correct our sense of distance, we still don't grasp the next betrayal. The sun is not just bigger than everything else. It dominates the solar system so completely that when we scale it down into something we can hold in our hands, the planets almost disappear. And that raises another question. If the sun were the size of a simple ball, what would the rest of the solar system really look like? Because once we see that, the familiar picture collapses for good. If we want to understand the solar system, we have to shrink it, not because it makes it smaller, but because it makes it honest. Because the real solar system doesn't fit in our mind the way a diagram does. It doesn't fit in a classroom. It barely fits in language. And this is where the story turns. Because the moment we scale the sun down into something we could hold, everything we thought we knew about the planets collapses. Not slowly, instantly. Let's build a scale our senses can finally hold. Let's say the sun is not a blazing sphere 93 million miles away, not 150 million kilometers away. Let's say the sun is something ordinary, a ball, a simple smooth ball, about 1/2 meter wide, about the size of a large beach ball. Now we can stand next to it, we can circle it, we can feel it. But then the universe punishes us for that comfort, because once we pick a sun, we can touch. The planets do not become clearer, they become harder to find. Here's the strange part. Most of us imagine Earth as a small ball next to a big ball, like a tennis ball near a basketball. But that mental picture is wrong by an almost embarrassing margin. In reality, the Sun is about 109 Earths across. 109. So if our Sun is a beach ball, about 50 centimeters, about 20 inches wide, then Earth is not a tennis ball. Earth becomes a peppercorn, a tiny bead, about 4 to 5 millimeters wide, small enough to slip between fingers, small enough to lose in carpet, small enough to drop in grass and never see again. And this is why our intuition fails, because our imagination wants Earth to be substantial. But the solar system does not reward human pride. Imagine this. We place our beach ball Sun at the center of a wide open park, and then we take our peppercorn Earth and we walk it out to the correct distance. At this scale, Earth does not orbit close. It orbits about 54 meters away, about 177 feet. That's more than half a football field. So we have a beach ball Sun, and far away, across open air, a peppercorn, and suddenly the solar system doesn't look like a neat family portrait. It looks like an empty field, with two objects that barely acknowledge each other. But that's not the whole story, because Earth is only the beginning. Once we accept Earth as a peppercorn, the rest of the planets don't become more dramatic. They become more disturbing, because most planets are not the giants our childhood diagrams implied. Mercury? At this scale, it's a grain, smaller than our peppercorn Earth. Mars? Smaller too. Venus comes close to Earth's size, but still, it's not a world in your hand. It's another bead. Even Jupiter, our so-called giant, doesn't save the picture. Jupiter is enormous compared to Earth, yes, but compared to the Sun is still about 10 times wider than Jupiter. So in our park model, Jupiter becomes a modest sphere, something like a large marble or small orange, depending on the exact sunball size we chose, and it would sit very far away, in darkness and distance we're not ready for yet. This is why scale breaks our intuition, because we want the planets to be the main characters, but in the solar system, they are supporting roles. Now we reach the fact that quietly rules the entire solar system. The Sun is not just bigger, it is almost everything. By mass, the Sun contains about 99.8% of all the mass in the solar system. 99.8%, meaning if we could place the entire solar system on a scale, the Sun would be the weight, the planets would be dust. This is why the solar system is not truly a system of planets, it's a system of one star, and everything else that failed to become a star. And this is where everything changes, because when one object holds almost all the mass, it also holds almost all the power. We tend to talk about size as if size defines importance, but in space, gravity is the real authority. Gravity doesn't care how big something looks. Gravity cares about mass and distance. This is the same truth behind Einstein's work, that mass shapes the structure of reality around it, and in the solar system, the Sun shapes almost everything: the paths of the planets, the speed of their motion, the way comets return after centuries, the way spacecraft fall inward or fight to escape. NASA mission teams don't launch into a simple void. They launch into a gravitational landscape, a kind of invisible architecture shaped overwhelmingly by one object: the Sun. And here's the disturbing part. Once we see how dominant the Sun is and we realize the planets are not holding themselves in place, they are constantly falling around the Sun. Orbit is not balance. Orbit is controlled descent, a perpetual fall that never reaches the ground. But then another misunderstanding appears. We hear Sun is biggest, so we assume gravity is simply about being large. Except that's not how it works. A planet can be huge and still not control much if the Sun's pull overwhelms it. A planet can be relatively small but still hold moons tight if they're close enough. Gravity is a relationship. It is not a trophy. It's not about who is biggest in a lineup. It's about what mass does to space and how distance weakens or strengthens that influence. This is why the same solar system can contain a sun that dominates everything, a Jupiter that can reshape paths and trap objects, and an Earth that still holds a moon in orbit. Not because Earth is powerful in absolute terms, but because in the moon's local neighborhood, Earth is the main source of gravity. And that brings us to the next unsettling truth. Because once we understand the sun's dominance, we start asking the wrong question. We stop asking, how big are the planets? And we start asking, how far apart are they really? We've all seen animations where a spacecraft glides from planet to planet like it's hopping stones across a river. But real space travel is a war against distance and timing, even at speeds that would obliterate anything on Earth. Speeds faster than a rifle bullet. A spacecraft still spends most of its journey doing something that looks almost insulting. It coasts, it drifts, it moves through blackness where nothing changes hour after hour, day after day. Because in this scale model, the planets are not lined up like neighbours, they are scattered, and the space between them is not a gap, it's a void that swallows human intuition. Now, let's make it personal. Hold the idea in your hand. Picture you holding a peppercorn between your fingertips. That peppercorn is Earth, and somewhere far away, across a field you have to walk, a beach ball. Sun sits in silence. If you drop that peppercorn into the grass, it disappears. That is how small our world really is compared to the star that holds it. And if that makes you feel uneasy, good. Because discomfort is the first honest reaction to true scale. So here's what we carry forward. The solar system is not defined by the planets. It is defined by a star that holds almost all the mass and therefore shapes almost all motion. Size is what our eyes notice. Gravity is what reality obeys. This is why the sun doesn't just sit there. It rules, quietly, constantly, and everything else, every planet, every asteroid, every comet, moves inside the sun's gravitational claim. But that only explains who dominates. It doesn't explain something even more haunting. Because when we place the sun as a beach ball and Earth as a peppercorn, a new problem appears, a problem our mind hates. At our scale, Earth is a peppercorn, but it's also alone. Not metaphorically, physically, because when we start placing the next objects in the model, we realize something that should not feel true, but is. Near-Earth space is not crowded, it is not busy, it is not a tight local neighborhood of nearby worlds, it is a quiet, expanding emptiness. And the closest major companion Earth has, the Moon, is not right there, like the night sky suggests. It's shockingly far. So the next door we have to open is this. If Earth is only a peppercorn in a field, then where do we put the Moon? And why does the space between them feel so much larger than our eyes ever admitted? From down here, the Moon feels familiar. It rises like a slow lantern. It follows us home. It hangs over rooftops like it belongs to our street. But this is where our brain commits its most convincing lie. Because the Moon is not near. The Moon is far in a way that should feel impossible, and yet we rarely feel it. And that's the problem, because if we can't feel the distance to the closest world beyond Earth, then we have no chance of feeling the solar system. The average distance from Earth to the Moon is about 384,400 kilometers, about 238,855 miles. That number is correct, but it is not real to our senses. So our mind does what it always does with overwhelming scale. It shrinks the truth until it fits inside a comfortable picture, and the night sky helps it, because the Moon looks big, it looks close, it looks like we could reach it with the right ladder. Except something was wrong, because when NASA sent humans there, when they actually crossed that distance, the trip didn't take hours, it took days, and that should bother us, because it exposes the real geometry we live inside. Here's the strange part. Our moon is close enough that we can see its craters with a small telescope, close enough that it dominates our tides, close enough that it feels like part of Earth's identity, but it's also far enough to create a gap that shatters intuition. Scientists measure the moon's orbit precisely, and it isn't a fixed number, it swings. At its closest, it can be around 363,300 kilometers, about 225,700 miles. At its farthest, it can be around 405,500 kilometers, about 252,000 miles. Even our nearest neighbor refuses to sit still, and yet we still imagine it as a nearby ornament. Picture this. We go back to the scale that makes the solar system honest. We place the sun as a beach ball, about 50 centimeters, about 20 inches wide. Earth becomes a peppercorn, about 4 to 5 millimeters wide, and Earth's orbit sits about 54 meters away, about 177 feet. Now, where does the moon go? This is where the truth snaps into focus. The moon would orbit our peppercorn at roughly 14 centimeters away, about 5.5 inches, about the width of a child's hand. So in the small model, the moon seems close, but in the real solar system, that hand width becomes 384,000 kilometers, 238,000 miles of emptiness. And this is the first time we can feel the betrayal, because the same relationship can look tiny in a model and still be a monstrous gulf in reality. The moon is far in a very specific way. It sits roughly 30 Earth diameters away, 30 Earth widths. If Earth were a basketball, the moon would be a tennis ball, sitting about 7 to 8 meters away, roughly 25 feet. That's not right next to it. That's across a room, across a driveway, across the space where things feel separate. And this is why the moon matters, because it teaches us a lesson the solar system keeps repeating. Space doesn't separate worlds politely. It tears them apart with distance and calls that normal. Now let's make the emptiness undeniable. There's a fact astronomers love because it sounds like a trick, but it's just scale. If we line up the planets of our solar system except Earth, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, all of them can fit side by side in the gap between Earth and the moon. And after placing every one of those worlds in a straight line, we would still have space left over. Thousands of kilometers, thousands of miles. This is what the moon's distance really means. Not romance, not symbolism. A corridor of emptiness wide enough to hold worlds, and yet, when we look up, we feel none of it. Our eyes don't measure distance directly. They measure angles. They compare objects to familiar reference points. But in the sky, we lose all reference. No street corners, no known sizes, no nearby landmarks. So the moon's half-degree width, about the width of a fingernail held at arm's length, becomes a lie our brain accepts as closeness. And this is biological. Our depth perception works best at human distances, a few meters, maybe a few dozen meters. Beyond that, the world starts to flatten, so the sky becomes a dome in our mind, a ceiling, a painted surface. But it isn't a ceiling, it's a direction into open space. And once we accept that, a darker truth appears. Because the moon is not the only thing that's far. Near-Earth space itself is almost empty. We say space is right above us, and in one sense, it's true. But the moment we step beyond the atmosphere, the distance begins to unfold. The International Space Station orbits around 400 kilometers up, about 250 miles. That sounds close, but even that close is already beyond ordinary human experience, and the gap above it keeps going. Geostationary orbit, where many communication satellites live, sits around 35,786 kilometers up, about 22,236 miles. That's nearly the width of Earth itself, stacked upward. And above that, more emptiness, not filled with traffic, not crowded with objects, just a thin scattering of machines inside a volume of space so vast it swallows the word near. This creates a bigger problem, because if near-Earth space is already so empty, then travelling through it is not like driving through a city. It's like crossing an ocean at night, with no lights, no roads, no sense of speed. When NASA sent Apollo crews to the Moon, they didn't crawl. They moved at speeds that would feel violent on Earth. After leaving low Earth orbit, their spacecraft travelled at roughly 11 kilometers per second, about 25,000 miles per hour. 25,000. At that speed, we could cross a major country in minutes. We could cross the United States from coast to coast in a breath. And yet, even at that speed, the Moon is still days away. About 3 days for Apollo. Because the distance is not a trip, it's a gulf, and the spacecraft isn't simply aiming like an arrow at a target, it's falling through gravity, guided by physics, timing, and precise trajectory. This is why spaceflight feels slow, not because we lack power, but because the solar system is built to punish the idea of quick, and the universe offers us a simple measurement that never lies: light. Light travels about 300,000 kilometers per second, about 186,000 miles per second. Even light doesn't make the Earth-Moon gap feel small. A signal travelling at light speed takes about 1.3 seconds to go one way to the Moon, about 2.5 seconds for a round trip. So even a conversation, spoken as radio, has a delay, a faint pause, a reminder that the Moon is not hovering above us. It is separated by real distance, real time, real emptiness. Now, let's make it land. Hold your hands apart, about the width of a child's hand. That's the Moon's distance in our scale model. Now let that same gap expand in your mind until it becomes 384,000 kilometers, 238,000 miles, a handspan that turns into a corridor wide enough to fit worlds. If you feel your stomach tighten, that's your intuition trying to resist the truth. Because this is what scale does. It makes the familiar unsettling. The Moon dominates our sky because it's large in angular size, not because it's near. It's bright because sunlight is intense here, close to the sun. It's easy to see because it reflects light well and fills a noticeable patch of sky. But if we could step away, far enough to see Earth and the Moon together as points, we'd witness something that feels almost cruel. Two small bodies, separated by vast blackness, bound to each other only by gravity and time. And that's why our mental picture has been wrong. Because night sky viewing is intimate, it makes the cosmos feel close enough to touch, except the Moon is the closest proof that it isn't. So, here's what we keep. The Earth-Moon system is not a tight pair. It's a relationship stretched across a gulf. And once we see that gulf, the next truth becomes unavoidable. If this is what near looks like, then the rest of the inner solar system is going to break our intuition completely. Because Mercury, Venus, Mars, they are not sitting nearby, like neighbouring houses. They are separated by emptiness so wide that most of the journey is silence and coasting and waiting. And that raises the next question. If the Moon, our closest companion, already lives across a corridor wide enough to hold worlds, then what happens when we try to cross from one planet to another? Because the inner planets aren't close together. They only look that way from inside the lie. When we look at the inner solar system, it feels almost crowded. Mercury, Venus, Earth, Mars, 4 worlds, 4 names we've known since childhood. And in our imagination, they sit close together, like nearby towns on the same map. But this is where the solar system quietly humiliates our intuition. Because these planets are not neighbours. They are islands, and the water between them isn't water. It's a vacuum so wide it fractures the idea of near. And once we see that, the inner solar system stops feeling like a lineup. It starts feeling like an empty, silent desert with a few scattered stones. We've all seen the diagram, a neat row of planets, even spacing, everything visible at once. But that picture is a translation, not a reality, because the moment we try to keep distances honest, the planets stop being planets on the page. They become specks, and the empty space becomes the main character. So let's keep using the scale that finally tells the truth. Our sun is a beach ball, about 50 centimetres, about 20 inches across. At that scale, Earth isn't a globe. Earth is a peppercorn, and Earth's orbit sits about 54 metres away, about 177 feet. Now, we can ask the question that breaks the inner solar system open. Where do the other inner planets actually go? Picture this. We place our beach ball sun at the centre of a park. Now we start walking outward, placing planets where they truly belong. Mercury comes first, not right next to the sun, like a tight circle in a diagram. At this scale, Mercury's orbit sits about 21 metres away, about 69 feet. Venus comes next. Its orbit sits about 39 metres away, about 128 feet. Then Earth at 54 metres, 177 feet. Then Mars, finally, out at about 82 metres, about 269 feet. Now stop. Look at that. In a park-sized model, the inner solar system is already spread across real walking distance. And in the real solar system, those steps become something else entirely. Because one step in this model hides tens of millions of kilometres, tens of millions of miles. And this is where the story cracks open. Because we haven't even tried to travel between these worlds yet. Here's the strange part. Even when we talk about the distance to Mars or the distance to Venus, those distances aren't fixed. The planets are not parked. They are moving, always, orbiting at different speeds, on different paths, at different times. So sometimes the inner planets line up in ways that look convenient. They appear close in the night sky. They shine brightly, like reachable destinations. But that visual closeness is an illusion built by perspective, because space doesn't care how close two dots look on a black background. Space cares about the real distance between them, and those distances swing wildly. Earth and Venus can come relatively near, on the order of tens of millions of kilometres, tens of millions of miles. Earth and Mars too can sometimes approach to around 55 million kilometres, about 34 million miles. That's the closest story we love to tell ourselves. But most of the time, Mars is much farther, often more than 200 million kilometres, more than 120 million miles away. And this is what our diagrams never show. They show a neat, static arrangement. But the real inner solar system is a moving puzzle, and that puzzle controls what we can do, and when we can do it. If we could stand above the inner solar system and look down, we wouldn't see a crowded neighbourhood. We would see huge arcs of nothing, thin paths, vast gaps. The planets themselves would look almost insulting, tiny beads on enormous invisible tracks. This is not poetry. This is geometry. Even near Earth, interplanetary space is so empty that the best vacuum chambers humans build on Earth still struggle to match it. There is no traffic, no lanes, no signposts, just sunlight, magnetic fields, sparse particles, and silence. And this emptiness creates a problem that our brains hate. Travel is not about going to the next object. Travel is about crossing the emptiness between orbits. When we imagine space travel, we imagine a rocket burning the whole way, like an airplane engine pushing against air. Except there is no air. So spaceflight becomes something stranger, a few powerful moments, and then long quiet drifting. NASA mission planners know this intimately. A spacecraft leaves Earth with a burst of energy. Then, for most of its journey, it is coasting, falling through the sun's gravity, following a path that physics allows. The engines don't roar the whole time. The ship doesn't push forward through space like a boat. It is guided by gravity and timing. Because the inner solar system is not a road, trip. It's a precision drop into a moving target. And this is why the emptiness matters. Because empty space doesn't slow you down. But it also doesn't help you. It just waits. From Earth, we look up and see planets as lights. A bright point for Venus, a reddish point for Mars. And our brain does something automatic. It treats that sky as a flat surface, a dome, a ceiling. So planets feel like stickers on the same dark wall, close together, almost touchable. But that's not reality. That's biology. Our eyes were built for depth at human distances, meters, not millions of kilometers. So we are trapped in a kind of sensory illusion. The inner planets look like they share the same stage, while they are actually scattered across a volume of space large enough to swallow entire civilizations without leaving a trace. Now, here's where it becomes unsettling. Spacecraft can move incredibly fast. A typical interplanetary trajectory can involve speeds of tens of kilometers per second, tens of thousands of miles per hour. At about 20 kilometers per second, about 45,000 miles per hour, we could cross a city in seconds. We could cross a country in minutes. We could cross Earth in less than half an hour. And yet, even at those speeds, the inner solar system refuses to feel small, because if a spacecraft left Earth heading toward Mars, the trip is still measured in months, often around 6 to 9 months depending on the mission profile and timing. 6 to 9 months. Not because we're slow, but because space is huge. At these speeds, we can cross countries in minutes, yet crossing the gap to Mars still takes most of a year, and that's the point. The distances are so vast that even extreme speed becomes ordinary. But then the universe adds another twist. Even if Mars is closer on a given day, that does not automatically mean we should launch, because space travel is not just distance, it's choreography. Earth and Mars are both moving around the Sun. So a spacecraft doesn't just aim at where Mars is now, it aims at where Mars will be months from now. That means timing becomes everything. This is why missions depend on launch windows, not because we lack technology, but because physics demands efficiency. The most fuel-efficient paths often involve transferring from one orbit to another along a carefully shaped arc. And for Mars, these favourable alignments repeat on a schedule. Roughly every 26 months, about 2 years and 2 months, Earth and Mars return to an alignment that makes the journey more practical. This is why we can't treat Mars like a destination we visit any time. Mars is not a nearby city, it's a moving world we must intercept. And every missed window is a reminder that the inner solar system is not built around our convenience. So what do we learn when we finally hold the true scale? Mercury isn't just a quick hop closer to the Sun. Venus isn't right next door. Mars isn't the next stop. Even inside the so-called inner solar system, the gaps are already immense. The inner planets are separated by emptiness so wide that most of what exists between them is nothing we can see. And this explains something that should have always been obvious. We have sent robots to these worlds, yes, but every journey was an act of patience, of calculation, of human minds trying to thread a needle through a moving cosmic machine. This is why it matters. Because once we understand the distances between the inner planets, we stop thinking of the solar system as a shelf of objects. We start seeing it as what it really is, a vast structure defined by space itself. Now place yourself in the model. You're standing in that park. Behind you, the beach ball sun sits silently at the center. You can't feel its heat now because it's just a ball, but in reality, it's the furnace that rules everything. You look to your left and imagine Mercury out at 69 feet, 21 meters. You turn and imagine Venus farther out. You turn again and imagine Earth at 177 feet, 54 meters. Then you walk and finally imagine Mars almost 300 feet away, 82 meters. Now let the model dissolve. Let those steps stretch until they become tens of millions of kilometers, tens of millions of miles, and feel what that does to the word near. Because this is the first time many of us truly realize it. Even our local neighborhood is mostly absence, but we're still not ready for what comes next. Because after Mars, our imagination expects something dramatic, a dense minefield, a chaotic region packed with rocks, danger, and constant collisions. Movies trained us to fear it. But the truth is colder. The next great region of the solar system, the asteroid belt, is not an obstacle. It's almost nothing. So the next question becomes unavoidable. If the inner planets are already separated by emptiness, then what does it mean that the asteroid belt is mostly empty too? And why did we ever believe it was crowded in the first place? When most of us hear the words asteroid belt, our mind doesn't picture science. It pictures a warning, a cockpit shaking, rocks spinning past the window, a desperate pilot threading a ship through chaos. It feels inevitable, like the solar system placed a minefield between the inner worlds and the giants beyond. But this is where everything changes, because the asteroid belt is not a wall, it's not a trap, it's not even crowded. In reality, the asteroid belt is almost nothing, and that truth is more unsettling than the Hollywood version, because it forces us to face what the solar system really is, not a busy place filled with obstacles, a vast emptiness with a few scattered survivors. We've been trained to imagine the belt as a thick swarm, a region so dense that travelling through it means constant near misses. But scientists don't describe it that way. NASA describes the main belt as a region between Mars and Jupiter, and even in their own teaching materials, the emphasis is on how spread out it is. Space.com puts it plainly too. The belt is huge, and the chance of randomly striking an asteroid is almost vanishingly small. They even quote New Horizons principal investigator Alan Stern, saying it's far less than 1 in a billion. So we have a contradiction. Our culture tells us dense danger. Science tells us empty distance, and that contradiction is the whole story. The word belt makes it sound like something tight, like a ring you could point to. But the asteroid belt is not a thin band. It's a region, a wide volume of space between Mars and Jupiter, spanning roughly 2 to 4 times the Earth-Sun distance. And that phrase, 2 to 4 times, is where our intuition fractures. Because Earth is about 150 million kilometers from the Sun, about 93 million miles. So, 2 to 4 times means we're talking about roughly 300 million kilometers to 600 million kilometers. From the Sun, about 186 million miles to 372 million miles. That's not a narrow ring. That's a vast zone, so wide it dwarfs the distance between entire worlds. And inside that zone, the material is thin, so thin that the belt's total mass is only about 3% of the Moon's mass. 3%. That means even if we gathered every asteroid together into one place, we still wouldn't get anything close to a planet. And that raises another question. If there are millions of asteroids, how can the belt still be almost nothing? Picture this. We take the emptiness seriously for once. We imagine the asteroid belt not as a swarm, but as a sky-sized room. Now we place asteroids inside it, the way nature actually does. On average, the distance between asteroids in the main belt is around 965,600 kilometers, about 600,000 miles. 600,000 miles. That's more than 2 times the distance from Earth to the Moon. So the truth is brutal. Even in the asteroid belt, the typical asteroid is not surrounded by rocks. It's surrounded by vacuum in every direction for distances that swallow the imagination. This is why spacecraft don't weave through the belt. They cross it the way a ship crosses an ocean, not dodging constant obstacles, but moving through a region so open that the real challenge is navigation, power, and time, not collisions. This is the part that feels almost like a cosmic joke. We've sent spacecraft through the asteroid belt many times, not by luck, by geometry, because the belt is so huge and its objects are so spread out that crossing it is usually uneventful. Space.com highlights exactly that. Hollywood close calls aren't how it works, and the odds of hitting something are tiny, and when a spacecraft does get close to an asteroid, it's not because the belt forced the encounter, it's because mission planners aimed with extreme precision, because to meet an asteroid in that emptiness, you have to choose one. You have to hunt a small moving body across millions of kilometers, millions of miles, and arrive at the same place at the same time. That's not dodging danger, that's threading a needle in the dark. So why did we ever believe the belt was crowded? Because the crowded version is emotionally satisfying. It gives space a familiar kind of danger, like a storm or a battlefield. It makes the solar system feel like an action scene. But the real solar system doesn't threaten us with constant impact. It threatens us with something colder: distance, silence, time, and emptiness is harder to film. Emptiness doesn't move. Emptiness doesn't explode. Emptiness just keeps going. So movies fill it with rocks. And our brains accept that filled version because it feels like something we understand, except something was wrong, because the real belt measured and mapped doesn't match the myth. And once we accept that, we start seeing the deeper pattern. The asteroid belt is not a barricade, it's a record, a population of leftovers that never became a planet, scattered across a region shaped by gravity and time. Wikipedia notes that much of the belt's mass is concentrated in just a few bodies: Ceres, Vesta, Pallas, and Hygeia, and that overall, the material is thinly distributed. So the belt isn't a pile, it's a memory of early solar system history, broken pieces, survivors, fragments that never merged, and the emptiness between them is not a failure, it's the rule, because the solar system doesn't build tight clusters, it builds wide separations, it builds lonely objects orbiting inside enormous volumes of nothing. And this is why our misunderstanding matters. If we think the belt is crowded, we imagine the outer solar system as a dangerous gauntlet. But if we understand the belt is mostly empty, we realize something more disturbing. The emptiness doesn't stop, it grows. Now bring it down to a human scale. Imagine you're standing on an asteroid, just rock beneath your feet, sunlight sharp and unfiltered. You look out, and you expect to see other asteroids nearby, but you don't. In most directions there is nothing. No neighbors, no movement, just black space, stretching for hundreds of thousands of miles, hundreds of thousands of kilometers, before the next significant object might even exist. That is what the asteroid belt really feels like, not chaos, isolation. But then, a bigger truth appears. If the asteroid belt, the most famous obstacle in our imagination, is mostly empty, then the next step outward becomes terrifying for a different reason. Because beyond the belt, we don't just meet another planet, we meet the first world that feels like a different category of reality: Jupiter, a planet so massive that it reshapes orbits, captures objects, and dominates its region gravitationally. So the question we have to ask now is this: if the asteroid belt is almost nothing, what does it mean that Jupiter is so powerful that it can sculpt the solar system itself? Because once we step into Jupiter's realm, the scale stops being merely vast. It becomes overwhelming. Up until now, the solar system still feels familiar. Small worlds, close enough to imagine, close enough that our mind can pretend the distances are manageable. But then we step beyond the asteroid belt, and we meet the first true giant. Jupiter doesn't just look bigger, it feels like the solar system suddenly changes genre, because the moment Jupiter enters the frame, the inner planets stop feeling like the center of anything. They become a distant memory. And this is where everything changes, because Jupiter is not simply a planet out there in the dark. Jupiter is a gravitational authority, a presence so massive that it reshapes the architecture of our entire neighborhood. We've heard the word gas giant so many times it's lost its meaning. So let's make it physical. Jupiter is about 143,000 kilometers wide, about 89,000 miles wide. Earth is about 12,700 kilometers wide, about 7,900 miles wide. That means Jupiter is a little more than 11 Earths across, but across is still too gentle. Because volume is where the truth becomes disturbing. Jupiter has enough space inside it to hold roughly 1,300 Earths. 1,300. If we tried to stack our world inside Jupiter like tiny beads in a hollow sphere, we would keep pouring Earths in, and Jupiter would keep swallowing them. And still, Jupiter isn't the main character of the solar system. The Sun is, but Jupiter is something else. Jupiter is the first object we meet that feels like it could have been a star, and failed. And that failure left behind a planet powerful enough to bend the rest of the solar system around it. Here's the strange part. We grow up thinking the solar system is a collection of planets, like a group, like a balanced set. But Jupiter breaks that idea immediately. Jupiter contains about 2.5 times the mass of all the other planets combined, not just the inner planets, all of them. So when we talk about the planets, we're not talking about equals. We're talking about one dominant planet and a scattered remainder. And that dominance matters because gravity doesn't care about beauty. Gravity cares about mass. This is the same lesson Einstein gave us in a deeper way. Mass shapes the behavior of space itself. And in our solar system, Jupiter is the first planet that truly demonstrates that power. Picture this. We return to the model that keeps humiliating our intuition. Our Sun is a beach ball, about 50 centimeters, about 20 inches wide. Earth is a peppercorn. Now we walk to Jupiter. In the real solar system, Jupiter orbits at about 5.2 times Earth's distance from the Sun. So, in our park model, where Earth sits about 54 meters from the Sun, Jupiter sits about 280 meters away, about 920 feet. That's almost a kilometer scale. Walk. A long, quiet walk. And during that walk, there's almost nothing. No objects we can point to, no visible structure, just open space and distance. This is why Jupiter feels like a border, because the moment we try to place it accurately, we realize the inner solar system is not the main stage, it's the opening act. Even in real numbers, Jupiter refuses to stay close. On average, Jupiter is about 778 million kilometers from the Sun, about 484 million miles. From Earth, the distance changes constantly. Sometimes Jupiter comes relatively near, around 600 million kilometers, about 370 million miles. Other times it retreats toward nearly 1 billion kilometers, around 600 million miles. That isn't a trip, that's a gulf. And if we don't feel that gulf, we don't understand what comes next. Because beyond Jupiter, the distances don't just increase, they begin to dominate story. At Earth, sunlight is a daily certainty, a bright, warm force that defines life. But Jupiter sits more than 5 times farther from the Sun than we do, and light fades with distance in a ruthless way. By the time sunlight reaches Jupiter, it's only about 1/27th as intense as it is here. 1/27th. So imagine taking the light of a bright afternoon and dimming it until only a thin fraction remains. Not darkness, not night, but something like a permanent late dusk, a colder, thinner daylight. And this is where the solar system starts to feel like deep space, because warmth fades, energy fades, and the sun begins to look less like a sky-filling source of life and more like a bright star in a black ocean. We already learned that sunlight takes a little over 8 minutes to reach Earth, but at Jupiter, even light starts to feel delayed. Light from the sun takes about 43 minutes to reach Jupiter on average. 43 minutes. That means the sunlight touching Jupiter right now began its journey almost an hour ago. And when we send a radio message, a signal moving at light speed, the conversation becomes slow. Depending on where Earth and Jupiter are in their orbits, a one-way message can take roughly half an hour to nearly an hour. So we're not just separated by distance, we're separated by time, and that creates a deeper mystery. If information itself can't travel instantly, what does it mean to operate a spacecraft out there? This is where space travel stops feeling like exploration and starts feeling like endurance. A spacecraft can leave Earth moving faster than any bullet, faster than any plane, and still, the trip to Jupiter takes years. NASA's Juno mission launched in 2011 and reached Jupiter in 2016. 5 years. Not because the spacecraft was crawling, but because the solar system is enormous and fuel is precious. Even when we move fast, distance stretches the journey into a different scale of time. This is the same psychological shock we keep running into. We picture going outward like traveling across a map. But out here, every destination is moving, every path is curved, and gravity is the unseen terrain. Now we reach the real reason Jupiter matters. Jupiter doesn't merely exist in the solar system, it edits the solar system. Its gravity influences asteroids, carving patterns into the belt. It holds whole swarms of asteroids locked in stable positions, Jupiter's Trojan asteroids, sharing its orbit like silent companions. It tugs on comets and can pull them inward, reshaping their paths. This is why scientists talk about Jupiter family comets, because Jupiter doesn't just watch objects pass by, it captures them into new destinies. Sometimes Jupiter deflects objects away from the inner solar system. Sometimes it sends them toward it. And that uncertainty is part of Jupiter's power. Jupiter is not simply a shield. It is not simply a threat. It is a gravitational gatekeeper, constantly rearranging the traffic of small bodies. And we have seen the evidence with our own eyes. In 1994, comet Shoemaker-Levy 9 broke apart and slammed into Jupiter, leaving scars larger than Earth. That wasn't a movie scene. That was our solar system revealing its violence, and Jupiter took the blows like a world-sized target. Planetary scientists at NASA and universities don't talk about Jupiter casually, because Jupiter is a laboratory, a world of extreme physics, a planet with storms larger than continents, a magnetic field strong enough to create radiation environments that challenge spacecraft design. This is why missions like Galileo and Juno mattered so much, because if we want to understand how planets form, how atmospheres behave, how gravity shapes a system, we study the first true giant, and Jupiter, more than any other planet, forces us to think in the language of scale, mass, distance, time. Now, imagine this. Just once make it personal. Imagine you are floating far from Earth, looking back toward the inner solar system. The sun is still bright, but smaller. And in the distance ahead, Jupiter hangs like a pale, enormous lantern. Not because it glows, because it reflects what little sunlight reaches it. And you feel something you never feel on Earth. A sense that you are approaching an object so massive that your path is no longer yours. Your trajectory is being negotiated by gravity, quietly, relentlessly. That is what Jupiter does. It turns space into terrain. But then comes the bigger truth. If Jupiter is already this far, if light itself is already taking nearly an hour to cross the gap, if missions already take years, then what happens beyond Jupiter is not just more of the same. Because beyond Jupiter, the distances expand into a scale that starts to detach from human life. Beyond Jupiter, the sun becomes weaker. The warmth fades. The travel times stretch, and the solar system begins to feel less like a collection of planets and more like a long, thinning thread of isolated worlds. And that brings us to the next illusion, because the next planet outward, Saturn, feels familiar. It feels close. It feels almost intimate because of one beautiful detail we can see even from Earth. Rings. But here's the strange part. Those rings, so iconic, so delicate, are about to distract us from the truth again. Because Saturn is not close. Saturn only looks close. And the moment we measure it honestly, the feeling collapses. So the next question is unavoidable. If Jupiter is the first true giant, massive enough to reshape the solar system, then how far away is Saturn really? And why does it still feel like it belongs to our neighborhood? Saturn feels like something we know, not because we've been there, not because it's close, but because it has rings. A signature so clean, so recognizable, that our brain treats Saturn like a familiar landmark in the sky, like a lighthouse we could point to from anywhere on Earth. But this is where the solar system quietly deceives us again. Because Saturn's beauty makes us forget the scale. It makes a world almost 1 billion miles away feel reachable. And that illusion is dangerous, because once we believe Saturn is familiar, we stop respecting the distance that defines it. We can see Saturn through a small telescope. We can even see the rings with something you could set up in a backyard. And our mind takes that as proof of closeness. But sight is not distance. Sight is only brightness and angle. Saturn shines because it's large and reflective, and because sunlight still reaches it. But the actual separation between us and Saturn is a different kind of reality. One, our senses were never built to hold, and this is why Saturn is the perfect illusion. It looks intimate, while it remains unimaginably far. Here's the strange part. Saturn's rings look massive, and they are. The main ring system spreads out to a width of roughly 280,000 kilometers, about 174,000 miles across. That is almost the distance from Earth to the Moon. So, in terms of width, Saturn's rings are enormous. But then the universe adds a twist. Those rings are also unbelievably thin. In many places, they're only tens of meters thick, on the order of 10 to 100 meters, roughly 30 to 300 feet, a structure as wide as a planetary-scale disk, with the thickness of a building. That contrast should feel impossible. A cosmic sheet, a razor-thin architecture drawn around a giant planet, and our brain doesn't know what to do with that. So it does what it always does with scale. It compresses the truth into something comfortable. It turns the rings into a big, solid thing. But the rings aren't solid. They're countless particles, ice and rock, each one orbiting Saturn like a tiny moon in a vast, thin swarm. And once we understand that, the rings stop being decoration. They become evidence. Evidence that the solar system is built from extremes, and those extremes don't care about what we can imagine. Picture this. Imagine Saturn's rings as a vinyl record laid flat on a football field. The record is huge, stretching nearly from one end to the other. Now imagine the thickness of that record isn't the thickness of plastic. It's thinner than a sheet of paper, so thin you'd struggle to see it from the side. That's Saturn's rings, a structure that looks like a giant object, but behaves like a thin, delicate plane of moving debris. And that fragility is part of why Saturn feels close, because our brain thinks fragile things must be nearby. But Saturn is not nearby. Saturn orbits the Sun at roughly 9.5 times Earth's distance. So even in the best case alignment, when Earth and Saturn line up on the same side of the Sun, Saturn is still about 1.2 to 1.3 billion kilometers away. That's about 750 to 800 million miles. Let that settle. 750 million miles, 800 million miles. We can say the number. But our mind can't hold it. So we need to translate it into something human. If we drove a car at highway speed, about 100 kilometers per hour, about 60 miles per hour, without stopping, to reach Saturn at its closest, the drive would take well over 1,000 years, more than a millennium. You could begin that drive in the early Middle Ages, before modern science, before modern nations, and you still wouldn't arrive today. And that's only the closest Saturn ever gets. Most of the time, it's farther. This is why Saturn's rings are a trap. They make something ancient and distant feel like it belongs to our neighborhood. So why does it still feel familiar? Because Saturn behaves like a steady presence in our sky. It returns year after year. It moves slowly compared to the inner planets. It doesn't flash past like a meteor. It sits there, patient, quiet, like it's waiting for us. And our mind translates steady into near. But Saturn isn't steady because it's close. It's steady because it's far, and its orbit is immense. It takes Saturn about 29.5 Earth years to complete one orbit around the Sun. That means Saturn has been completing one full year of its own, while nearly 3 decades pass on Earth. Saturn's pace is not the pace of a neighbor. It's the pace of a deep time world, a world that makes human timelines feel brief, and that creates a deeper mystery. If Saturn is this far and this slow, what does distance really do to the solar system beyond this point? At Earth, sunlight takes a little over 8 minutes to reach us. That already should feel strange, but at Saturn, the delay becomes heavier. Sunlight takes about 75 to 85 minutes to reach Saturn, about 1 hour and 15 minutes. So the light touching Saturn right now left the Sun more than an hour ago. And if we send a radio command to a spacecraft near Saturn, radio traveling at the speed of light, that message also takes on the same scale of delay, roughly an hour or more to arrive, depending on where Earth and Saturn are in their orbits, and then another hour for the response to return. So even communication becomes slow, not because our technology is weak, because distance is real. Distance turns every action into patience. Distance turns every decision into commitment, and this is why scientists and mission teams treat Saturn with a different kind of respect. At Saturn, we don't just explore space, we negotiate with time. Now we reach the part our bodies understand instinctively. Heat. Sunlight doesn't just fade visually, it fades physically. At Saturn's distance, sunlight is roughly 1% as intense as it is at Earth, about 1/90th. So imagine standing in a bright room, and someone turns the lights down until only a thin fraction remains. Not darkness, but a weakened daytime, a colder radiance, a sun that still shines but no longer dominates your world the way it dominates ours. This is why the outer solar system begins to feel like a boundary, because beyond a certain point, the sun stops feeling like a life-giving presence and starts feeling like a distant star. And yet, Saturn's rings keep pulling us back into comfort. They look clean, they look organized, they look like something designed. But Saturn is not a designed world. It's a violent, dynamic system ruled by gravity. The rings are shaped by Saturn's immense pull and by the gravitational influence of its moons. Tiny disturbances become patterns, gaps appear, sharp edges form. It's not decoration, it's physics made visible, and the planet beneath those rings is not gentle. Saturn is a gas giant with winds that can reach extreme speeds, storms that can wrap around the planet, and a magnetic environment that can be harsh to spacecraft. This is the uncomfortable truth Saturn teaches. Familiarity is not safety. Beauty is not closeness. Clarity is not comprehension. And if we let Saturn's image lull us into comfort, we miss what it's really telling us. Now imagine you're holding a thin silver bracelet. From a distance, it looks solid, like a single object. But when you bring it close, you can see it's made of many small links. Now take that feeling of something that looks simple until you approach it and apply it to Saturn. Because Saturn's rings are our bracelet in the sky. They look like one clean structure, but in reality, they're countless pieces, each one obeying gravity, each one in motion. And you only realize that when you stop trusting the picture and start trusting the scale. So here's what Saturn gives us. Saturn is the last planet that can still feel familiar through a telescope. It still has a recognizable face. It still feels like part of a solar system we can casually imagine. But that's an illusion. Because in numbers, Saturn is already far enough to break. Our sense of travel, our sense of communication, our sense of sunlight as warmth, and our sense of time as something we control. At Saturn, the solar system starts to widen into something colder, wider gaps, longer delays, weaker light, and that shift matters. Because Saturn is the threshold where the sun begins to lose its emotional dominance, where our star starts to look ordinary. A bright point, a source, yes, but no longer a presence you feel on your skin. But then, the universe has one more twist, because Saturn is still not the edge. Beyond Saturn, the distances stretch so far that they don't just challenge intuition, they break it. Uranus and Neptune orbit so deep in the solar system that sunlight becomes thin, cold, and unfamiliar. From out there, the sun doesn't rule the sky. It becomes a bright star, one of many, hanging in a black ocean. So the question we have to face next is this. If Saturn already feels distant, what happens when we go so far that the sun stops feeling like the sun at all? Because beyond Saturn, our solar system doesn't just get bigger, it starts to dissolve into deep space. There's a moment in the solar system where our mental map fails completely. Up close, the sun feels like a ruler, a furnace at the center, a presence that defines day, warmth, and life. But if we keep moving outward, past Saturn, past the comfort of familiar names, we reach a distance so vast it does something disturbing. The sun stops feeling like the sun. It becomes a star, not a metaphor, a literal change in how it appears and how it matters. And this is where our intuition fractures. Because Uranus and Neptune are not farther planets, they are the threshold where the solar system begins to turn into deep space. At Earth, we live about 1 AU from the Sun, about 150 million kilometers, about 93 million miles. That's already too large to feel. But Uranus orbits at roughly 19 times that distance, about 2.9 billion kilometers, about 1.8 billion miles from the Sun. Neptune is farther still, around 30 times Earth's distance, about 4.5 billion kilometers, about 2.8 billion miles. Those numbers don't just sound big, they break the part of the brain that tries to picture a place. And this creates a bigger problem. If we can't feel the distance, we can't feel what that distance does. Because distance isn't empty math. Distance changes light. Distance changes heat. Distance changes time. Picture this. We return to the scale that keeps exposing the truth. Our sun is a beach ball, about 50 centimeters, about 20 inches wide. Earth is a peppercorn. Earth orbits about 54 meters away, about 177 feet. Now we walk to Uranus. Uranus sits at about 19.2 times Earth's distance. So in this model, Uranus is about 1,037 meters away, about 1.0 kilometers, about 3,400 feet. That's about 2/3 of a mile. Now keep going. Neptune sits at about 30 times Earth's distance, So Neptune lands about 1,620 meters away, about 1.6 kilometers, about 5,300 feet. That's about 1 mile. In the model, Uranus and Neptune are not just farther out. They are a long, quiet walk away across open space where almost nothing changes. And in the real solar system, that walk becomes billions of kilometers, billions of miles. This is why the outer planets feel like a different regime, because distance begins to dominate everything. Here's where the story cracks open. Sunlight doesn't fade gently, it fades brutally. The farther you go, the more that light spreads out, thinning across space. At Uranus, sunlight is about 1/360th as intense as it is on Earth. At Neptune, it's about 1/900th. So imagine taking a bright, warm afternoon and turning the sunlight down until only a thin fraction remains. Not night, not darkness, just a weak, cold daylight. A sun that still exists, but no longer feels like it rules. And this is why Uranus and Neptune are so psychologically important. They force us to confront a fact we don't like. The solar system is not filled with the sun's warmth. The solar system is filled with the sun's influence slowly dying with distance. Now we reach the unsettling visual truth. From Earth, the sun dominates the sky. It's not a point. It's a disk so bright we can't look at it. But from Uranus and Neptune, the sun shrinks. It becomes smaller in the sky by the same factor as distance. At Uranus, the sun looks about 19 times smaller across than it does from Earth. At Neptune, about 30 times smaller across. And when a disk shrinks like that, it stops feeling like a presence. It starts feeling like an object, a bright point, a star that happens to be ours. And this is where the emotional architecture changes, because the sun's physical power is still there. Gravity still holds these worlds, but the sun's sensory dominance fades. Light becomes weak, heat becomes scarce, and the solar system begins to feel like what it really is, a star system embedded in a larger galaxy, not a cozy neighborhood built for human life. At Earth, sunlight takes a little over 8 minutes to reach us. That already means we see the sun as it was 8 minutes ago. But out here, the delay becomes heavy. At Uranus, light takes roughly 2 hours and 40 minutes to arrive. At Neptune, roughly 4 hours. So when sunlight touches Neptune, it began its journey earlier the same day. And when mission teams send commands to spacecraft near Neptune, they don't pilot them in real time. They send instructions and wait, because even light can't make distance feel small anymore. At this range, space isn't just big, space becomes slow. And then, the universe adds another twist. Time. Uranus takes about 84 Earth years to complete one orbit around the Sun. Neptune takes about 165 Earth years. That means Uranus experiences one full year, while a human lifetime passes on Earth. Neptune experiences 1 year across multiple human generations. This is not poetic exaggeration. This is the clockwork of the solar system, a place where the word year stops being a comfortable human unit and becomes a reminder that our lives are tuned to one small warm orbit near a star. And this is why the outer solar system feels less like a map and more like deep time. Let's anchor that to something we can feel. If you were born when Neptune last completed a full orbit, you wouldn't just be old today, you would be a name in history. Neptune's last full year began before electric grids lit cities the way they do now, before modern computing shaped daily life, before much of the modern world took its current form. A Neptune year is not a calendar year, it's a historical era. And that raises another question. What does it mean to explore a place where the natural rhythms move on generational timescales? By the time we reach Uranus and Neptune, we begin to notice a change that isn't just about numbers. It's about feeling. The inner solar system still feels like a system of worlds with sunlight as a constant, But out here, the sun becomes weaker, smaller, colder. The space between planets grows wider. Travel stretches into decades for many missions, and the emptiness becomes more obvious. Not because there are no objects, but because the volume of space becomes so enormous that objects become rare. Uranus and Neptune are the point where the solar system starts to look less like a set of planets and more like a long, thinning frontier, a gradual fade from the warmth of a star into the dark structure of the galaxy. We don't have to guess how hard it is to reach this realm. We've done it. NASA's Voyager 2 launched in 1977. It reached Uranus in 1986, about 9 years later. It reached Neptune in 1989, about 12 years after launch. 12 years. A childhood to adulthood, a mission lasting longer than many careers. And that's with a spacecraft moving faster than anything humans have ever driven, flown, or thrown on Earth, coasting through vacuum guided by gravity. This is what distance does. It turns exploration into patience. Now imagine you're standing on a world out near Neptune, not imagining its winds or its clouds, just the sky. You look up and you search for the sun, and you find it, bright, sharp, but small, not a blazing disk, a star. And for the first time, you would feel something you don't feel on Earth, the sense that home is not nearby, not in distance, not in time. Home is a bright point in the sky, and everything around you is cold space, stretching outward with no sign that it ever ends. That is the emotional reality of the outer solar system. So here's what this region forces us to accept. Uranus and Neptune aren't just faraway planets. They are the boundary where sunlight becomes thin and weak. The sun shrinks into a star-like point. Light travel time becomes hours, and orbital periods stretch across human lifetimes. They show us the solar system's true nature. Not a cluster, a gradient, a slow transition from warmth into deep space. And once we see that transition, we can't unsee it, because the next lie we carry is even bigger. Most people quietly assume Neptune is the edge, the last real place. After that, emptiness. But that's not true, not even close. Beyond Neptune, the solar system continues into the Kuiper Belt, into distant icy worlds like Pluto, into objects scattered across the dark, a region where planet matters less than distance, and where the sun's influence still reaches, faint but real. So the next question is unavoidable. If the sun has already become a star by the time we reach Neptune, then what does it mean? That the solar system keeps going anyway? And what else is waiting in the cold beyond the last planet we can easily name? For most of our lives, the solar system ends at Neptune, not because we were taught that directly, but because every diagram quietly suggests it. 8 planets, a neat outer edge, a final blue world, and then emptiness. But this is where the story turns, because Neptune is not an ending. Neptune is a doorway, and beyond that doorway, the solar system becomes stranger, not through fantasy, but through real, measured geography, a belt of frozen worlds, a population of objects older than our civilizations, and distances so wide they make the word planet feel almost irrelevant. Neptune orbits about 4.5 billion kilometers from the Sun, about 2.8 billion miles. That's already a number that doesn't fit inside human intuition, but our mistake is thinking, okay, that's the edge. Except something was wrong, because astronomers didn't stop finding objects. They kept finding them farther out. Not one, not two, an entire region, a vast zone of icy bodies orbiting in deep cold, beginning roughly around 30 times Earth's distance from the Sun, and stretching outward to around 50 times Earth's distance, and that region has a name that sounds gentle, the Kuiper Belt. But the Kuiper Belt is not gentle, It is the solar system revealing that it never had a clean border. Picture this. Imagine the inner solar system as the bright center of a city. Close streets, familiar neighborhoods, worlds we can name without thinking. Then we travel outward, past the asteroid belt, like leaving downtown, past Jupiter and Saturn, crossing into wide suburbs, past Uranus and Neptune, where the streetlights thin out. And then, after Neptune, we expect open wilderness. But instead, we find the outskirts don't stop. We find a sprawling ring of frozen debris, more like distant towns scattered across a huge, dark countryside. Not packed together, not crowded, but undeniably there. That's the Kuiper Belt, a region, not a line. A reminder that the solar system doesn't end neatly. It fades. The Kuiper Belt isn't a glittering ring you can see from above. It's not a halo of visible objects. Most of it is dark, cold, small, and incredibly far away. But it's populated. A huge number of icy bodies, some only a few kilometers across, some hundreds of kilometers across, and a few large enough to become worlds with geology, atmospheres, seasons, and history. And the most famous object out there is the one that still triggers an argument in almost every conversation about space: Pluto. Pluto is not a distant version of Earth. Pluto is a Kuiper Belt world, and its orbit tells us everything about why the solar system beyond Neptune doesn't behave like the solar system we grew up imagining. Pluto orbits at an average distance of about 5.9 billion kilometers, about 3.7 billion miles from the Sun. That's roughly 39 times Earth's distance. But Pluto's orbit isn't a neat circle, it's stretched. So Pluto sometimes comes closer, down near 29 times Earth's distance, and sometimes retreats farther, out near 49 times Earth's distance. So even Pluto refuses to stay in one place. It swings through deep space like an object on a long, cold tether. And here's the strange part. Pluto's orbit actually crosses the distance of Neptune. That should feel impossible. A smaller world crossing the path of a giant planet. Except Pluto doesn't collide, because Pluto is locked into a gravitational rhythm with Neptune, a stable pattern that keeps them from meeting. This is what the outer solar system really is. Not tidy lanes, but resonances, gravitational choreography. And once we understand that, Pluto stops being a weird planet. It becomes evidence that the solar system is governed by distance first and labels second. For decades, Pluto was just a point of light, a name, a debate. But then NASA's New Horizons changed everything. It flew past Pluto in 2015, and Pluto stopped being an icon and became a real place. Mountains of water ice, a surface with surprising complexity, a thin atmosphere, and then New Horizons kept going, because the mission itself was a confession that Pluto was never the end. It was one landmark inside a much larger frontier. In 2019, New Horizons flew past a Kuiper Belt object called Arakoth, a small, ancient body shaped like two lobes gently fused together. And what did that tell us? That the Kuiper Belt is not just a region of leftovers, it is a region of history, preserved, cold, waiting. But the Kuiper Belt isn't the outer limit of structured objects, because beyond it, the solar system gets stranger. We reach the scattered disk, a population of objects with orbits so stretched and tilted that they look like they've been thrown outward, scattered by gravitational encounters over billions of years. Some of these objects swing far beyond the Kuiper Belt, then return inward again. Their orbits are long, eccentric, uncomfortable for our intuition, because they don't form a neat belt, they form a messy, extended population, objects that still belong to the Sun, but live at distances that begin to dissolve our sense of what belonging even means. And then, in that darkness, astronomers find something even more unsettling: extreme objects, detached worlds with perihelia, so far from the Sun that they don't behave like typical Kuiper Belt bodies at all. These are not speculative in their existence. These objects are observed, but their origins lead into deep questions we need to handle carefully, because out here the solar system becomes a crime scene of gravity, and the evidence is written in orbit shapes. Now we have to address the word that keeps hijacking the conversation: planet. Pluto used to be called the 9th planet. Now it's classified as a dwarf planet. That debate matters culturally, it matters emotionally. But physically, the outer solar system doesn't care what we call Pluto. Distance is the real category. Because beyond Neptune, we enter a regime where sunlight is weak, temperatures collapse, orbital periods stretch into centuries and beyond, and objects become sparse across enormous volumes of space. In that regime, the question isn't, is it a planet? The real question is, how far from the Sun does it live? Because distance defines everything out there: light, heat, time, and even the type of orbit an object can hold. Labels are human. Distance is physics. We can build the most powerful spacecraft in history. We can throw it outward at speeds that would cross continents in minutes. And still, the outer solar system makes those speeds feel small. New Horizons, one of the fastest spacecraft ever launched, still took about 9.5 years to reach Pluto. 9.5 years. That's the length of a childhood. That's the length of a decade. So even when we move fast, distance turns travel into time we can't ignore. And this creates a deeper mystery. If the Kuiper Belt begins around 30 AU and stretches to around 50 AU, what happens beyond 50? Because the solar system doesn't just continue, it thins, and then it fades into something almost invisible. Now imagine you're out there, somewhere near Pluto's orbit. You look back toward the Sun. It's still bright, but it no longer fills your sky. It no longer feels like a presence. It feels like a hard white star. And you realize something quietly disturbing. From here, Earth is not far away. Earth is lost. Not lost as in unknown. Lost as in swallowed by distance. A world reduced to invisibility. A single, life-bearing planet hidden inside a glare you can't even resolve. That is what distance does. It doesn't just separate places, it erases them from the senses. So where does the solar system actually end? Here's the uncomfortable truth. The solar system doesn't end where planets stop. It ends where the Sun stops being able to hold space as ours. And that boundary isn't a line we can draw with a marker. It's a gradual weakening, a fading. Even out here, beyond Neptune, the Sun's gravity still holds objects in orbit. It still shapes their paths. But the farther we go, the more fragile that hold becomes, because the Sun's influence competes with the galaxy itself, its tides, its passing stars, its distant gravitational pressure. So the Kuiper Belt and the scattered disk are not the edge. They're the beginning of the fade, the solar system transitioning from a structured system of planets into a long, thin halo of distant bodies that still whisper, "We belong to the Sun," even as the galaxy begins to pull at them. So here's what we carry forward. Neptune is not an ending. Beyond Neptune we find the Kuiper Belt, an extended region of icy worlds, Pluto 1. Landmark within that region, with an orbit that defies our tidy diagrams, the scattered disk, objects thrown into long, stretched paths by gravity, and a truth that keeps repeating: distance matters more than labels, because in the outer solar system, distance determines reality. What we can see, what we can reach, how long a year lasts, how warm sunlight feels, whether a world is stable or only temporarily held, and that leads to the next threshold, because even the Kuiper Belt is not the final structure. Beyond it, the solar system stretches into a realm so distant that billions of kilometers stops being the unit. The distances become so vast, we start measuring in fractions of a light year. A region of ancient ice and long-returning comets, a halo that may extend tens of thousands of AU from the Sun. So the next question is the one that forces our minds to go quiet. If the solar system doesn't end at Neptune and doesn't end at Pluto, how far out does it go before the Sun's gravity finally dissolves into interstellar space? Because the next region isn't just far, it's almost a light year wide. There's a comforting idea we carry, that the solar system is a family of planets, ending neatly at Neptune, and then beyond that, emptiness. But that picture is a lie our diagrams tell to keep the page from tearing, because if we follow the Sun's reach into the dark, the solar system doesn't end like a fence, it ends like fog. It thins, it quiets, it dissolves, and hidden inside that fade is a structure so vast it almost sounds fictional. A sphere of ancient ice surrounding everything we call home, the Oort cloud, almost a light year wide, not a place we can point to in the sky, a boundary we can only feel through what it throws toward us. Let's be precise. The Oort cloud is not a ring like Saturn's, it's not a belt like the Kuiper belt, and it's not a visible wall marking the edge of the solar system. Scientists describe it as a giant spherical shell, a thick bubble of icy, comet-like bodies surrounding the Sun, the planets, and the Kuiper belt objects. And here's the strange part, we haven't photographed the Oort cloud directly. It's too far, too dim, too sparsely populated across an unimaginable volume. So the Oort cloud is a structure we infer, like a shadow we can't see, but can measure by what it does, because it has a signature: comets. In 1950, the astronomer Jan Oort proposed something unsettling. Some comets arrive from so far away that only a huge reservoir, far beyond the planets, could explain them. Not the Kuiper belt, not Jupiter's neighborhood, something vastly deeper, a distant spherical swarm that still belongs to the Sun, but barely. That idea became the Oort cloud, and once we accept it, the solar system stops being where the planets are. It becomes the full territory where the Sun can still hold objects in orbit. Now we have to talk numbers. NASA describes the Oort cloud occupying space roughly between 5,000 and 100,000 AU from the Sun, and NASA's scale infographic puts the inner edge of the main Oort region potentially as close as about 1,000 AU, with the outer edge around 100,000 AU. 1 AU, 1 astronomical unit, is the average Earth-Sun distance, about 150 million kilometers, about 93 million miles. So 1,000 AU is about 150 billion kilometers, about 93 billion miles, and 100,000 AU is about 15 trillion kilometers, about 9.3 trillion miles. Those numbers don't just feel large, they feel wrong. Because our brain expects the solar system to be a collection, the Oort cloud forces us to see it as a volume, a spherical territory so enormous that even outer and inner begin to lose meaning. Here's where the story truly shifts. At these distances, astronomers stop reaching for kilometers and miles. They start reaching for light years, because 100,000 AU is about 1.6 light years from the Sun. That means the Oort cloud isn't out there past Pluto, it's out there approaching the space between stars. NASA even notes that beyond the outer edge, the gravity of other stars begins to dominate over the Sun. So when we say, almost a light year wide, we're not being poetic. We're describing a physical border where the solar system starts to become negotiable. Picture this. Imagine the Sun as a bright lantern on a field at night. Close to the lantern, everything is obvious. You can see the ground, you can navigate, you know where you are. Now walk away. The lantern is still bright, but it shrinks. Its warmth stops reaching you. Its light stops defining your world. Eventually, the lantern becomes just a point, still real, still there, but no longer dominant. That's what happens to the Sun in the Oort cloud. It doesn't turn off, it just stops feeling like it rules. And this is where our solar system starts transitioning into interstellar space, not by crossing a line, but by fading into a regime where other stars can interfere. Now we reach the Oort cloud's fingerprint, long-period comets. These are comets with orbital periods longer than 200 years, and some can reach up to 1 million years. 1 million years. That number is so large it stops sounding like time and starts sounding like geology. To anchor it in something we can feel. 1 million years ago, early humans weren't building cities. Homo sapiens had not yet appeared. Vast chapters of human ancestry and culture still lay ahead. So when an Oort cloud comet returns, it's not coming back after a long time. It's returning after civilizations rise and vanish, like ripples disappearing on water. And this creates a deeper mystery. What could possibly disturb an object so far away that it falls inward toward the sun after spending most of its existence in deep cold? This is where movies have damaged our intuition again. The Oort cloud is not a dense minefield of ice. It is not a place where a spacecraft would weave between giant boulders. It's more like this: a vast sphere of mostly empty space, with icy objects separated by distances so large that crowded becomes meaningless. The danger isn't collision. The danger is distance itself. Distance that turns travel into decades and communication into waiting. Now we touch the most unsettling part. Gravity doesn't stop at Neptune. It doesn't stop at Pluto. It continues outward, growing weaker but still shaping motion. And in the Oort cloud, that weakness becomes the story. NASA describes the Oort cloud as the region where the sun's gravitational dominance begins to give way to the influence of other stars. Out there, objects are only lightly bound. They can be nudged, and those nudges can come from the slow tidal pull of the Milky Way or the gravity of passing stars moving through the galaxy. So the Oort cloud isn't just a storage room. It's a fragile halo, constantly threatened by the larger environment of the galaxy, and when that halo is disturbed, comets can be redirected inward. Not because the comet decides to visit the inner solar system, because gravity reorganizes the distant dark. Now imagine you're out there, far beyond Neptune, far beyond Pluto. There's no sunlight the way we know it, no warm glare, just a black sky and a sun that looks like a hard white star, and you realize something quietly brutal. From here, the solar system doesn't look like a system of planets. It looks like a fading influence, a single star trying to hold onto a halo of ancient ice, while the galaxy presses in from every direction. Out here, home isn't behind you. Home is a point of light. So where does the solar system end? Not at Neptune, not at Pluto, not even at the Kuiper Belt. Scientific consensus often treats the solar system's outer boundary as extending out to the Oort cloud, because that's where the sun's gravity still shapes a reservoir of objects. And beyond the Oort cloud's outer edge, the sun's grip is no longer the dominant force. That means the end of the solar system is not a wall. It's the distance where the sun can no longer reliably claim objects as ours, where an icy body can be stolen by a passing star, where the Milky Way's tides can reshape orbits, where the solar system becomes porous. And that's the cosmic truth the Oort cloud reveals. Our system dissolves gradually into the galaxy, but then the universe adds one more twist, because there's another edge we need to understand. Not an edge of gravity, an edge of wind. The sun blows a constant stream of particles outward, the solar wind, creating a bubble in space, a protective region called the heliosphere. And unlike the Oort cloud, we've actually sent spacecraft to the frontier of that bubble. So the next question becomes unavoidable. If the Oort cloud is the farthest reach of the sun's gravity, where is the boundary where the sun's breath ends and true interstellar space begins? There's a quiet lie we carry around without noticing, a lie that feels harmless because it feels familiar. We look up at the night sky, and it seems close enough to touch. A few bright points, a soft black dome, a clean, simple neighbourhood. But that picture collapses the moment we ask one honest question. Where does the solar system actually end? Not where our drawings stop, not where our attention stops, where the sun's influence finally fails. Because out there, beyond the last planet, there isn't a wall, there isn't a gate, there is only a fading pressure, a thinning wind, and a boundary so invisible we can only find it by listening to ghosts of radio signals, crawling across space at the speed of light. And this is where the story fractures, because the edge of our system is not where most of us think it is, and what comes next is unsettling. When we say solar system, we usually picture planets, a neat lineup, orbit after orbit, a tidy diagram, but the truth is more disturbing. The solar system is not defined by objects, it's defined by influence, by gravity, yes, but also by a constant outflow from the sun itself, a flood of charged particles and magnetic fields pouring outward in every direction. NASA describes this as a protective bubble created by the sun, made of particles and magnetic fields that extends well past Pluto. That bubble has a name, the heliosphere, and it is not static. It swells, it trembles, it interacts with the galaxy like a living thing, breathing against an ocean of interstellar space. Here is the strange part. We live inside this bubble our entire lives, yet we cannot see it. We can't look at it the way we look at clouds. We can only measure it through instruments, through plasma, through magnetic fields, through the slow, stubborn work of NASA and JPL engineers and scientists watching numbers change. And those numbers tell us something almost humiliating. Our cosmic home is not a set of planets. It's a thin, invisible boundary where the sun's wind finally loses a pressure war against the cold interstellar medium. Picture this. It's night. We're outside. A single campfire burns. Close to the flame, the air is warm. Smoke pushes outward. You feel protected inside that little sphere of heat. But the world around it is winter. Wind presses in, and there's a precise distance where the fire's warmth can't win anymore, where the storm takes over. That's the heliosphere. The sun is the campfire. The solar wind is the warmth and smoke pushing outward, and interstellar space is the storm, cold, dense, indifferent, and the boundary is real, even though it's invisible. For a long time, scientists suspected this boundary had structure, not just one line, layers, regions where the solar wind slows, compresses, heats up, then finally stops being dominant. One of those regions is called the termination shock, a place where the solar wind abruptly slows as it begins to collide with interstellar pressure. Voyager 2 reached that termination shock on August 30th, 2007, according to NASA's mission timeline. That date matters more than it seems, because it marks a point where the solar system stops feeling like a clean planetary map and starts feeling like a coastline, not land and water, but the sun's breath, meeting the galaxy's breath. And then the real problem appeared, because even after the termination shock, the sun's influence continues. The wind becomes turbulent, heated, distorted. A region NASA describes as part of the boundary system that must be crossed before entering interstellar space. So where is the true edge? That outer boundary has a name too. The heliopause. NASA defines it plainly. It's where the tenuous, hot solar wind meets the cold, dense interstellar medium. That sentence sounds clinical, but what it describes is violent in its own way. A collision of environments, a place where the sun stops being the loudest thing in the room, and for the first time, we have crossed it. Two spacecraft, built with 1970s technology, launched when many of us weren't even alive, have done something that sounds like mythology. They reached the boundary and went beyond it. NASA reports Voyager 1 crossed that boundary in 2012, and Voyager 2 crossed it on November 5th, 2018. Read that again. We didn't just theorize the edge, we measured it. We watched instruments change as the sun's wind dropped and interstellar space began. And the scale is where our intuition collapses. On the day NASA announced Voyager 2's crossing, they also gave a number that should make our stomachs drop. Voyager 2 was slightly more than 11 billion miles from Earth, about 18 billion kilometers, 11 billion miles, 18 billion kilometers. And even then, it wasn't gone. It was simply outside the heliosphere. And because light has a speed limit, NASA notes that information moving at the speed of light took about 16.5 hours to travel from Voyager 2 back to Earth. 16.5 hours for a single whisper. Now listen to what that means in human terms. You can fly across Earth in less than a day. You can cross continents while the sun is still up. But our farthest machines are so distant that even light, the fastest messenger the universe allows, needs most of a day to bring us a sentence, and Voyager 1 is even farther. NASA and JPL describe Voyager 1 as more than 15 billion miles away, about 24 billion kilometers, with a radio signal that takes around 22.5 hours to reach us. Almost a full day for a hello. So when we talk about space, we're not talking about a place. We're talking about delay. We're talking about distance so large that cause and effect begin to feel separated. Here's where our minds try to relax. We hear interstellar space, and we think, that's it, the solar system is over. But that's not the whole story. NASA is clear about this. Even after leaving the heliosphere, Voyager 1 and Voyager 2 have not left the solar system, because there's another boundary, defined not by solar wind but by gravity, a region where objects still belong to the sun, even if the sunlight is weak, even if the warmth is gone. NASA describes that outer boundary as being beyond the outer edge of the Oort cloud, a collection of objects still under the sun's gravitational influence, and the numbers here become almost cruel. NASA estimates the Oort cloud begins at about 1,000 astronomical units from the sun and may extend to about 100,000 astronomical units, 1,000 to 100,000. That is not a belt. That is a vast, thin kingdom of distance. NASA even gives us a timeline that feels like a warning. It would take about 300 years for Voyager 2 to reach the inner edge of the Oort cloud, and possibly 30,000 years to fly beyond it. 300 years. That's longer than many nations have existed in their current form. 30,000 years. That reaches back toward the edge of modern human behavior, before writing, before cities, before history as we usually tell it. And Voyager is still moving, still traveling, still not finished. So if we thought the heliopause was the end, we were still thinking in diagrams. And here's the moment you should feel it. If you could stand next to Voyager, out there beyond the heliopause, there would be no wind on your skin, no air, no sound, only the quiet pressure of radiation and the thin, hard fact that Earth is now so far away that your voice could never reach it. Not because you can't shout, but because there is nothing to carry the sound. And even if you could send a radio signal, you'd still be waiting almost a full day just to be heard. This isn't poetry. This is physics. And it forces a new question. If interstellar space begins just beyond our heliosphere, what does the galaxy look like compared to this? Now we widen the frame. We stop thinking like planet dwellers. We start thinking like astronomers. NASA sources commonly describe the Milky Way as about 100,000 light-years across. 100,000 light-years, and we don't even need to convert that into miles to feel the shock, because a light-year is already a unit that admits defeat. It's distance measured by the fastest thing in the universe. So let's translate it into a scale we can hold. The heliopause is on the order of about 100 astronomical units away. NASA notes the heliopause as the boundary where solar wind meets interstellar medium, and their Voyager results place this boundary far beyond the planets. The Milky Way is about 50 million times wider than that heliosphere scale. That number is our calculation, built from NASA's Milky Way size and the heliosphere boundary scale. And here's what that means in a simple mapping. If we shrank the heliosphere down so its radius was 1 meter, then the Milky Way would stretch about 50,000 kilometers, around 31,000 miles. That's more than the circumference of Earth. That's a galaxy so large that our entire solar system, even with its invisible bubble and its distant cloud of comets, becomes a point on a map that can't be labelled without zooming in. And this creates a deeper mystery, because the sun feels huge to us. It dominates our sky. It dictates our seasons, our days, our biology. But out there, the sun is just one star among hundreds of billions, and our home is a thin region of influence, brief, fragile, and surrounded on all sides by a galaxy that does not notice us. Scientists like Einstein showed us that the universe obeys rules that don't care about our intuition, and thinkers like Hawking reminded us that the universe is not obligated to feel human scale. This is one of those moments. Heliosphere is not a poetic idea, it's a measurable boundary. The Voyagers crossing it isn't symbolism, it's evidence. And the distance beyond it isn't just big, it is so vast that even our most successful machines will spend centuries and millennia just approaching the outer gravitational frontier of the sun. So when we ask, where does the solar system end and the galaxy begin? The answer is unsettling. They overlap. They fade into each other. The solar system doesn't stop like a fence. It dissolves like breath into winter air. And now we're left with something heavier than a number. If the solar system is mostly emptiness, if its true edge is defined by invisible forces, if even interstellar space is only the beginning of a longer exile, then what does home even mean in a universe like this? Because the final question isn't about distance anymore, it's about significance. And once we understand the true scale of the solar system, we can't unfeel what it implies about us. And that implication is where the story turns philosophical. We've been told a comforting lie, not with words, with pictures. We've been shown a solar system that looks like a tidy family portrait, a bright sun, a handful of planets, all lined up like beads on a string. But when we finally measure it, when we finally force reality to keep its proportions, the whole story collapses into one brutal truth. The solar system is not made of planets, it's made of distance. And once we understand that, everything about our place in the universe feels different. Start with something we all think we understand: the sun, the center, the source of warmth, light, and gravity. At our average distance, the sun is about 93 million miles, or 150 million kilometers away. That number is so clean we barely feel it, but try to feel it for real. Imagine driving a car toward the sun, non-stop, day and night, no traffic, no rest, no stopping. At highway speed, the journey wouldn't take days or weeks. It would take nearly 2 centuries to reach the sun, and that's just the first step. Because the deeper truth isn't just that the sun is far, it's that the sun is everything. NASA describes it plainly. The sun holds more than 99.8% of the mass in the solar system. So most of what we live inside is the gravity of one star, pulling on emptiness. Our brains evolved for forests, for rivers, for faces in the dark. We are built to judge distances that fit inside a day's walk. But space isn't a day's walk. Space is a structure so vast that even our best diagrams, even our most accurate animations, still shrink it into something our minds can tolerate. And this creates a quiet illusion. We start believing the solar system is a set of objects, when it's actually a field, a giant invisible architecture of gravity where planets are not the main feature. They're just what happens to be caught inside it. We often talk about cosmic loneliness like it's a metaphor, but it's not. It's a measurement. NASA explains that our heliosphere, the bubble carved out by the sun's solar wind, surrounds the planets like a protective shell. This is not poetry, it's physics, a star breathing outward, pushing back the interstellar dark. And then, eventually, that breath weakens. Out there, the sun's influence thins, and the solar system begins to dissolve into the galaxy's wider ocean. And that creates a disturbing thought. Even the boundary of home is not a wall, it's a fading gradient. Imagine this. You're standing in a massive stadium at night, so large you cannot see the far edges. The lights go out, and one person, somewhere in the distance, holds up a single phone screen. That's the sun, at the outer reaches. Not gone, still there, but reduced, not by weakness, by distance. Because distance doesn't just separate objects, it changes what they are to each other. It changes warmth into cold, brightness into a star-like pinprick, a neighborhood into an empty continent. And this is the part we rarely accept. The solar system is not a busy place. It's an enormous silence with a few bright exceptions. Now we come back to the uncomfortable center of this whole story. Earth, a planet we treat like a backdrop, a blue dot we assume will always be here. But here's what scale does to us. It forces us to see Earth not as a world, but as a thin outcome, a narrow balance. One planet, at the right distance from one star with liquid water on the surface, inside a system dominated by emptiness. And when we look outward, the numbers stop being comforting. NASA notes that even the nearest star system is still measured in light years, not in the units we use for the solar system. Proxima Centauri, our nearest stellar neighbour, sits about 4.25 light years away, roughly 40 trillion kilometres, or about 25 trillion miles. So if our entire solar system feels vast, the space between stars is something else entirely. It's not a gap. It's a different category of distance. We often talk as if Neptune is the edge, but beyond it, the system continues into the Kuiper belt, into the scattered disk, and then outward toward the Oort cloud. NASA describes the Oort cloud as a giant swarm of icy bodies beginning around 5,000 astronomical units and reaching up to 100,000 astronomical units. Those numbers are so large they become almost meaningless until we translate them. At those distances, the sun's gravity is still real, but faint. Comets can take millions of years to return, and the shape of home becomes a ghostly sphere of distant ice, a final blur before interstellar space. So the solar system doesn't end like a fence, it ends like breath in winter air. And then comes the final compression of perspective. NASA describes the Milky Way as about 100,000 light years across. That is not just bigger than the solar system, it's bigger by a factor our instincts cannot hold. We are not living in the universe. We are living in a small gravitational pocket inside one galaxy, inside a star's thin domain, inside a system where distance is the main ingredient. This is why Einstein's universe feels so strange. Not because it's magical, but because it refuses to care about what our minds prefer. Space is not built for our intuition. It is built for physics. And now, just once, put yourself inside it. Tonight, when you look up, you may see the moon. It will look close, comforting, like it belongs to us. But you now know that close in space is a word we use when we want to feel safe. What you're really seeing is a reminder that even our nearest neighbour is far, and that almost everything in our solar system is separation. So when that sky feels familiar, remember, familiarity is the illusion. Distance is the reality. So what does the true scale of the solar system really mean? It means the universe didn't place us inside a crowded machine. It placed us inside a vast, quiet architecture where a star holds almost everything, and where the spaces between things are the dominant feature. It means Earth is not ordinary just because we live here. Earth is specific, rare in outcome, not in importance, and it means the loneliness we feel when we think about space isn't poetry, it's geometry, a measurable fact. But here is the final gentle twist. The same laws that keep Jupiter in orbit, that shape the heliosphere, that hold distant comets in a slow, ancient relationship with the sun, those laws also hold us, our atoms, our breath, our lives. We are not separate from the structure. We are a small part of it, thinking about itself. And maybe that's the most human truth of all. The solar system is mostly space, but inside that space, meaning still exists, not because the universe gives it to us, but because we are here long enough to notice the scale and quiet enough to finally feel it